Hi everyone. Today we're going to be completing our notes on 12.3 geometric sequences. I want to start with this warm-up. Given the sequence 8, 4, 2, 1, find the following. We're going to find the explicit definition and the recursive definition. So to start, I'm going to just list some of these terms. I know that the first term, A1, is equal to 8. The second term, A2, is equal to 4. A3 is 2. And A4 is 1. So I notice that this is not an arithmetic sequence. We're not adding or subtracting a common difference, but I do notice that there's a common ratio. Between successive terms, we are dividing by 2. Another way we can conceptualize this is multiplying by a half. Okay? So I know that because we have a common ratio, this can be modeled. If you're thinking of a different type of function, instead of modeling this using a linear function, this would be like an exponential function, which we know is in the form y equals a times b to the power of x. So by plugging in some values, if I were to plug in our first term and our second term, we can get two equations. Our first term, 8, is equal to a times b to the first power. And then plugging in our second one, we can get 4 is equal to a b to the second power. Okay. Solving both of these equations for a, we get a is equal to 8 over b, or a is equal to 4 over b squared. And then finally, if we were to set these equal to one another, substitute in for a, we would get, I'm going to move this up here, we would get 8 over b is equal to 4 over b squared, or 8b squared is equal to 4b. And then solving this for b, we get 8b squared minus 4b is equal to 0. Factoring, we get 4b times a quantity 2b minus 1 is equal to 0. We get 4b equals 0. 2b minus 1 equals 0. We get b is equal to 0, and b is equal to 1 half. Okay. Now, because b is the exponential base here, the exponential base cannot be equal to 0. So therefore, we only choose the solution b is equal to 1 half. So if b is equal to 1 half, well, plugging it back into the other equation, either of these equations, we get a is equal to 16. And so this can be modeled using y equals 16 times 1 half to the power of x. Now, using the sequence notation, we would write this as a sub n is equal to 16 times 1 half to the power of n. But know that the domain of a sequence is the natural numbers. We start with the first term. So if we want this exact same behavior, we're going to shift this over to the right 1, but that's going to change our initial value. So if we were to shift n over 1, we would have the quantity n minus 1 in the power, but that's going to change our initial value to be 8, which we know is the first term in the sequence. And then we get n minus 1. Okay, so this is going to be our explicit definition for an. The recursive definition is a little bit more straightforward. Any given term in the sequence, actually we need to define our first term. So again, a1 is equal to 8. So then an is equal to the previous term, a sub n minus 1, and then divided by 2, or multiplied by a half. Either of these representations are acceptable. Okay? So notice the difference between arithmetic and geometric sequences. Where arithmetic sequences have a common difference, our geometric sequences are going to have a common ratio. So this definition here, this explicit definition, notice that this 8 is our first term, and we're calling this a. And then this right here, instead of our common difference, this is our common ratio. So this is the ratio between successive terms, and we're going to call that r. All right? So let's go ahead and formalize this definition. A geometric sequence is a sequence in the form So if we were to write out this sequence, we would have our first term is a, our second term is a times r, our third term would be multiplied by that common ratio again, so ar squared, ar cubed would be the next term, and so on, okay? Where a is the first term, of the sequence, and R is the common ratio. Okay? R is the common ratio of the sequence. Okay. The nth term of a geometric sequence is given by a sub n is equal to a, our first term, times r to the power n minus 1. So notice that the second term of the sequence has a power of 1, the third term has a power of 2, fourth term has a power of 3. So it's always going to be 1 less than the number term in the sequence. So that's why we have n minus 1. Okay, so this is the explicit definition for the geometric sequence. Go ahead and flip the page. Let's find the first 5 terms of the geometric sequence where a is equal to 3 and r is equal to 2. So plugging it in, I know that a1 is going to be equal to 3. A2 is going to be 3 times our common ratio to the power of 2 minus 1, n minus 1. So this is equal to 3 times 2, or 6. A3 is equal to 3 times 2 to the 3 minus 1, which is 3 times 2 squared, or 3 times 4. That's equal to 12. You might see the pattern already. A4, we're going to double that again, so 24. And A5 is doubled again, 48. Okay? So the first 5 terms are 3, 6, 12, 24, 48. So again, that exponential base is our growth factor, so that tells us that we're doubling each time. So A1, so letter B, A1, A is 1 and R is negative 1/3. So then again, A1 is equal to 1, A2 is equal to 1 times negative 1/3 to the 2 minus 1. This is equal to just negative 1/3. A3 is equal to 1 times negative 1/3 to the power 3 minus 1. This is equal to negative 1/3, the quantity squared, which is positive 1/9. A4 is equal to negative 1/27th, and A5 is equal to positive 1/81st. Okay, so notice that the sign of the terms here is flipping. We go positive 1, negative 1/3, positive 1/9, negative 1/27th, positive 1/81st, and so on. So the sign is flipping, and that has to do with this negative common ratio. Okay, and then we just have the negative powers of 3. All right, so example 2, find the 8th term of the geometric sequence. So I know that the first term is 5, and then the common ratio, what are we multiplying by? Well, in order to find that, we can always just take the ratio of subsequent terms. So I'm going to take the ratio of the second and the first term, 15 over 5, and that gives me a common ratio of 3. So to find the 8th term, we can just plug in a sub 8 is equal to our first term, 5, times our common ratio, 3, to the power of 8 minus 1. This is equal to 5 times 3 to the 7th, which if we were to evaluate is 10,935. Okay? Example 3, the third term of a geometric sequence is 12 and the sixth term is 96. Find the 11th term. Okay, so I know that a sub 3 is equal to 12, the third term is 12, and I know that the sixth term, a sub 6, is equal to 96. So I know that a sub 3 times the common ratio 3 times is going to give me a sub 6. Okay, and the reason why I know that is because a sub 6 is 3 terms later in the sequence. And remember, subsequent terms in the geometric sequence are just multiples of the common ratio. So because we're moving 3 terms later in the sequence, from 3 to 6, we're going to multiply by the common ratio 3 times, and so we multiply by r cubed. So I know that a3 is 12, r cubed is equal to 96. Dividing both sides by 12, we get r cubed is equal to 8, or r is equal to the cube root of 8, or 2. So our common ratio is 2. So then we can plug this in. I'm going to choose, because we're finding the 11th term, I'm going to choose a6. So a6 is equal to get to the 11th term, we're multiplying by the common ratio 5 times. and that's equal to A11. So again, the difference between the 6th term and the 11th term is 5 multiples of the common ratio, so r to the 5th. So we get 96 times r to the 5th is equal to A11. And then I already know what r is, that's 2. So 96 times 2 to the 5th is equal to A11. 96 times 32. A11 is equal to 3072. Okay? All right, so now let's talk partial sums of a geometric sequence. So let's go ahead and define this. For the geometric sequence, which we know is defined as a sub n is equal to ar to the n minus 1, the nth partial sum is Sn equals a plus ar plus ar squared plus ar cubed, and so on. Okay, all the way up to ar n minus 1. So that's the nth term. Okay, so this would be the partial sum. This is given by Sn is equal to a times 1 minus r to the power of n all over 1 minus r. Okay, so this is our nth partial sum of a geometric sequence. One thing I just want to note that I didn't mention earlier is that just know that r cannot be equal to 1, because if r is equal to 1, well then we're just multiplying by 1 over and over and over. So there is no common ratio. This isn't a geometric sequence. This is just a constant term, just the sum of constants. Okay. I'm actually not going to circle that. I'm just going to put in parentheses. Okay, so the nth partial sum of a geometric sequence is Sn equals a, the first term, times 1 over r to the n, all over 1 minus r. Okay, so let's get some practice. Flip the page. Example 4. So find the sum of the first 10 terms of the geometric sequence. So I know that the first term is 2. Our common ratio is negative 6 over 2, or negative 3. And I want to find the 10th partial sum. So S10. This is equal to our first term, 2, times 1 minus our common ratio, negative 3, to the power of 10, all over 1 minus negative 3. Well, this is equal to 2 times, well, I know that 1 minus negative 3 to the power 10 is negative 59,048. And then that's all over 4, 1 minus negative 3. And this is equal to negative 29,524. Okay? Just a quick note that notice that the partial sum can also be rewritten using sigma notation. So we learned this in one of our previous notes. Sigma notation is the sum of terms from k equals 1 to the 10th term of our explicit formula, 2 times negative 3 to the n minus 1. Okay? I'm sorry, k minus 1. Okay, so we could write this using either notation here. So this is sigma notation or the partial sum Sn notation. All right, so now I want to talk about an infinite series. An infinite series is just a sum of all of the terms in the sequence. So if I were to say a series of the terms 1 through 5 in this sequence here, we would have 2, negative 6, 2 plus negative 6, plus 18, plus negative 54, plus the next term, right? An infinite series is just the sum of all of the terms in that sequence, so the infinitely many terms. So A1 plus A2 plus A3 plus A4, all the way up, never ending. So it's the infinite sum of series of terms. So an infinite series is in the form, using sigma notation, the sum of terms AK, where k starts at 1 to infinity. Okay. So let's take a look at example 5. Here you have a cake, and you want to eat it first by eating half the cake, and then eating half of what remains, and then eating half of what remains then, and so on. So if we have a whole cake, we eat half of it, now there's half remaining. We eat another half of what remains, and now there's a quarter remaining, and then an eighth remaining, and a 16th, and a 32nd remaining. And I want to know um, how much cake have we eaten after n servings? Okay, so I know that the partial sum Sn is equal to, well, when we first eat it, the first term, we eat half the cake. After that, we eat a fourth of the total cake. After that, we have eaten, so our third serving, we've eaten an eighth of the total cake, and then a 16th of the total cake, and so on. Okay? And I notice a pattern here. So our pattern here is that the denominator is those perfect powers of 2. And so eventually, our nth serving of the cake is going to be 1 over our power of 2, so 2 to the power n. And the partial sum of this is the sum of the n terms of the sequence. So then what happens to the amount of cake after you've eaten more and more servings? So in particular, what happens to the partial sum Sn as n approaches infinity? Well, because we are eating less and less within each serving, I'm getting closer and closer to completing the cake. Now, of course, I'll never finish the cake. If this is mathematically true, we're never going to finish the cake, but we're going to approach finishing the cake. Finally, we're going to get really close to finishing that cake. So as n approaches infinity, Sn approaches 1. We almost have completed one whole cake. Okay, consider the following series. Sn equals 1 plus 2 plus 4 plus 8 plus 16. So there are powers of 2. What happens as n approaches infinity? Well, we're adding numbers. So 1 plus 2 is 3, plus 4 is 7, plus 8 is 15, plus 16 is 31, and so on. It's just getting bigger and bigger and bigger. And this function does not approach a finite value. In fact, as n approaches infinity, Sn approaches infinity as well. It's just going to keep blowing up bigger and bigger and bigger. So we see two cases. As we increase the number of terms in the sequence, we can approach a finite value, or we can approach infinity or negative infinity. So now flip a page. Let's go ahead and talk about the sum of an infinite geometric series. There's a couple things we need to consider. So given the infinite geometric series, which again can be represented using sigma notation. So the sum of terms from k equals 1 to infinity of a times r to the k minus 1. I know that this can be written as a plus ar squared plus ar cubed, and so on, right? The sum of this infinite geometric series converges if the absolute value of r is less than 1, and then it diverges if the absolute value of r is greater than or equal to 1. Okay? So what do I mean by converges or diverges? Well, it converges, this series converges to a finite numerical value if the common ratio is less than 1. It diverges, meaning it blows up to infinity if the common ratio is greater than or equal to 1. So if it converges, yes, there's a way to mathematically find that single numerical value, that value. That sum is equal to S, which is A over 1 minus R. Notice that this is not Sn. That represents a partial sum. You can think of this as an infinite sum. So because we're not saying like S sub infinity, this is just the sum of the series. So as we go way, way out in the series, the sum will converge to a finite value, and that's represented as the first term over the quantity 1 minus the common ratio. Okay? So let's try some examples. Example 6. Determine whether the series converges or diverges. If it converges, find the sum. Okay, so for this first one, I know that the first term is 3, and our common ratio is equal to, well, our second term is 33/100ths, and I'm going to divide that by 3. I know that this is equal to, so dividing by 3 is the same as multiplying by a third, so that tells me that this is equal to 11/10. Okay? Well, because 11/10, for the absolute value of 11/10, is greater than 1, the series diverges. Okay? So that means that this series approaches infinity. Okay? Let's try another. Letter B. Here we have our first term is 7. Our common ratio, we do 5.6 divided by 7, the second term divided by the first term. Well, this is equal to 0.8 or 4/5. Since the absolute value of 0.8 is less than 1, the series converges. Okay, the series converges. So if we were to find out what it converges to, we would plug it in. S equals our first term, 7, over 1 minus our common ratio, 0.8. So this is equal to 7 over 0.2, which is equal to 35. All right, so this series, if we just keep adding terms in this series, it's going to get closer and closer to 35. All right, so these have been our notes on geometric sequences. We're going to get a lot of practice, so we'll see you tomorrow. Have a great day, everybody. Goodbye.